Hello and welcome to Cisco ACI Field Engineer Implementation Initial Fabric Configuration Module. The initial fabric configuration covers multiple steps: the initial configuration, the out-of-band configuration, NTP, access policies, which are external facing interfaces, ACI pools, domains, AEPs, VPC configuration in the ACI fabric, also troubleshooting access policies. We'll also discuss dynamic breakout ports and port profiles and port tracking policies. The initial configuration overview, if we were to actually, network engineers fully understand the layering concepts of the OSI reference model. While ACI presents a new paradigm, it is still possible to map the constructs of the ACI fabric to the ACI logical model to 7-layer OSI reference model architecture. Cisco ACI is not breaking the OSI model, it is transforming it. Let's just put it this way. As you can see, at physical layer 1, we have our access policies, AEPs, domains, which we will cover. Data link, layer 2, bridge domain, policy groups, VPC, port channels, interfaces, and encapsulation, VLAN and VXLAN. At the network layer, we've got our pervasive SVI, which is our bridge domain spread across all the leaf switches. Layer 3, private network, which are context, which is actually a VRF. It started off as being called a context, then a layer 3 private network, and now it's a VRF, although in the actual API, it's still labeled as a context. And then transport to application layer, you have contracts, graphs, application profile, and endpoint group. An initial overview on the initial configuration steps for an ACI fabric after the fabric discovery. So what we've done is we've plugged the APICs in and we've configured the fabric. Creating tenants, private networks, and bridge domains will be covered in later sections. Various tasks are performed by different administrative roles. Fabric-wide or tenant administrators create predefined policies that contain application or shared resource requirements. These policies automate the provisioning of applications, network-attached services, security policies, and tenant subnets, which put administrators in the position of approaching the resource pool in terms of applications rather than infrastructure building blocks. The application needs to drive the networking behavior, not the other way around. A tenant is a container for policies that enable an administrator to exercise domain-wide based access control. The fabric-wide administrator must create both the user tenant containers and the tenant administrators. The system provides the following 4 kinds of tenants. The infrastructure tenant is provided by the system and can be configured by the fabric administrator. It contains policies that govern the operation of the infrastructure resources, such as the fabric VXLAN overlay. The common tenant is provided by the system, but can be configured by the fabric administrator. It contains policies that govern the operation of resources accessible to all tenants, such as firewalls, load balancers, layer 4 through layer 7 services. The management tenant is provided by the system but can be configured by the fabric administrator. All of these can be configured by the fabric administrator. It contains policies that govern the operation of the fabric management functions used for in-band and out-of-band configuration of fabric nodes. A user tenant are defined by the administrator according to the needs of users. They contain policies that govern the operation of resources such as applications, databases, web servers, what have you. So as you can see, infrastructure admin runs the entire fabric, allows us to configure system-wide policies. The tenant admin allows us to create tenant policies, tenant constructs from a logical perspective. Out-of-band configuration. Out-of-band management network is a necessary part for providing access to the network infrastructure when the primary links to the devices are down. In the data center, OOB is generally provided via an exclusive OOB management VLAN, usually from another separate stack of switches. Like other Cisco Nexus devices, ACI elements provide a separate management port from each device to connect to the OOB management LAN. And you can see this in the pictures. There's the spine leaf OOB port, as well as on the APIC itself, the APIC OOB management interfaces that are dual homed. So you can actually see that It's not the network with the M, that's the SIMC interface. It is network ports 1 and 2. On the APIC, an OOB configuration creates an OOB management interface that is actually listed in the management tenant. Now, we talked about the different management networks a few minutes ago. Infrastructure VLAN is used for in-band APIC to switch node communication. It's non-routable outside the fabric. In-band management network is the tenant VRF created for in-band access to switch nodes. So generally, you would need to configure eventually an in-band management network, especially if control plane devices such as vCenter were going to reside inside the ACI fabric. The OOB management network, tenant VRF, is for the APIC and switch node dedicated management ports. An APIC controller has two routes to reach a management network. One is by using the in-band management, and the other is used by using the out-of-band management interface. In-band management, you can configure the in-band management connectivity to the APIC and the ACI fabric. You must first configure the VLANs that will be used by the APIC, and we'll talk about the other additional policy steps that you will have to do to configure those. Out-of-band management, a little bit more straightforward. You can configure out-of-band connectivity to the APIC and the ACI fabric. You only configure an out-of-band contract that's associated with an out-of-band endpoint group. The APIC out-of-band management connection must be 1 gig. The APIC controller always selects the in-band management interface over the out-of-band management interface if the in-band management interface is configured. So what you usually do is when you actually configure the APIC for the first time, you will configure it for out-of-band access, and then you will actually go in and swing that over eventually. So once you have both configured, it will prefer in-band management, but out-of-band management will still work. As of right now, the interface does not support IPv6 and cannot connect to an external IPv6 network through the out-of-band interface. In-band addresses can only be provisioned on the APIC controller only through a policy. Additionally, then in-band management addresses must be configured statically on each node. So in this case, we're creating a static node management address pool. So we create basically a pool of addresses, starting point, ending point, gateway, and mask. Network time protocol. It should actually be this should actually be the second thing you should automatically configure. You'll go to Fabric, Policies, Pod, and then under Date and Time. You can create your own date and time policy while leaving the policy default, but chances are we don't usually do that. A lot of customers that I've run into don't. But so you can usually just change the default policy as well, because it's very important that there be a reliable NTP server for later on for measuring latency and atomic counters. So you'll configure the date and time format. You'll configure the fabric pod policy to use your date and time policy. So the date and time policy is just a part of the fabric pod policy. So it's just another piece of the policy. If you want to view these commands on the APIC, you can do an NTP stat. And on the switches, you can do show NTP peers and show NTP peer status, or you can actually view your NTP servers in the GUI. And here's how you would set that configuration. You would set the system time, in this case in the APIC, which we would do initially. We would configure the fabric pod policies, date time format, date and time policy, add NTP providers, then create the pod policy group, select the default NTP policy, and then we would assign that pod policy group to the fabric pod profile. Time synchronization is critical to fabric operations. So usually there's not a whole lot of need to change these default policies. Date and time policy is very important. There might be usually ISIS, COOP policies, they're really not, you can just take the defaults and let the system actually manage that. That's what it's there for. BGP route reflector policy would be important because since the spines themselves from a layer 3 perspective, you have to be able to distribute routes within ACI fabric. So what you want is you want to have the BGP route reflector policy configured, so you will have to do that. And then you've got the management access policy, SNMP if you want to do monitoring, and then MACsec policy as well. So once you configure the pod profile, that will apply all those pod policies that we just saw that are fabric-wide. They're specified in the pod policy group. Pod profile default is created automatically. Pod selector default can be created automatically. So why would you need multiple pods? Well, you would need multiple pods for multi-site or multi-pod. There's no real need to have multiple pods in the actual same fabrics. Okay. You can then verify your node syncs with the NTP server by going to Fabric Policies, and NTP server. You can actually view those there. And we already talked about the commands NTP stat on the APIC, show NTP peers, and show NTP peer status. Access policies, configuring external facing interfaces. The infrastructure administrator configures ports in the fabric for speed, link aggregation control protocol, LACP, LLDP, and Cisco Discovery Protocol, many other things as well. Okay. In Cisco ACI, the configuration of physical ports is designed to be extremely simple, both for small and large-scale data centers. The underlying philosophy of Cisco ACI is that the infrastructure administrator categorizes these servers based on their requirements. Virtualized servers with hypervisor A connected at gig Ethernet, non-virtualized servers running OS are connected at a 10 gigabit Ethernet, etc. We want to be able to do this from a policy perspective. Cisco ACI provides a way to keep this level of abstraction when defining the connection of the servers to the fabric. The infrastructure administrator will prepare a template of configurations for servers connected with active standby teaming, port channels, VPCs, and bundles, and all the settings for the ports in a policy group. The administrator then creates the objects that select the interfaces of the fabric in ranges that share the same policy group configuration. So as you can see, we're not going to be doing these type of configurations at the port levels, but we are going to be setting the policies that we're going to use and then aggregate them into a policy group, which can then be bound to an application profile. And you'll see this in the actual next slide. The infrastructure administrator will do all those configurations. Okay, so what actually happens here, though, is that I've configured my LLDP, CDP, link level, and port channel policies. I bind them into what's called an interface policy group. So the interface policy group will determine how those ports will operate from a physical perspective. So if you get something from this class, understand the ACI access policy workflow. No traffic will flow unless all of these pieces are actually working together. The leaf switch profile are the leaves that are bound together. Usually these will be part of a VPC group. The leaf interface profile are the individual. The leaf interface profile discusses the actual interfaces that are part of the leaf switch profile. The interface policy group is the binding mechanism between the physical and the logical. So when we go over on the right-hand side, our VLAN pool feeds the physical domain, which is the physical device and what our EPGs are going to be tied to. And the AEP is the attachable entity profile, which provides the binding between the physical switch profile, interface profiles, and then the logical configurations that the AEP represents bound at the interface policy group. The policy model will manage the entire fabric, including the infrastructure, authentication, security, services, applications, and diagnostics. You can see here the logical constructs in the policy model define how the fabric meets the needs of any functions of the fabric. So this diagram is an illustration of the logical model hierarchy. The top of the ACI logical model is represented by the root or universe. The next hierarchical separation is the tenant. Each tenant will have at least one or more VRFs. Forwarding constructs are separated from connectivity constructs. Security and location separate them out. So so as you can actually see that we have the universe root, we have two tenants, we have VRFs and separate tenants, we have bridge domains and separate tenants, and so on. An external facing interface configuration, you can actually see the interface policies. The leaf interface profile, it has the interfaces. The leaf switch profile has the actual switches that are going to be bound to that interface. So interface policies are created globally. So link state, CDP, LLDP, port channel, doesn't matter. I just create a policy and use that globally. Leaf policy group governs the access ports, and will port channels, VPCs, or port channels or VPC override policy are going to be used. Fabric policies under the external access policies. So access policies configure external facing interfaces to endpoint devices. So here we define CDP, link level, speed, LLDP, on or not, port channel, what have you. You can also do miscabling protocol. It governs storage, compute, VMM, also layer 2, layer 3 connectivity as well. So access policies govern the operation of external facing interfaces that do not connect to a spine switch access ports that provide connectivity to resources. So those would be all those resources, layer 2, layer 3, storage, compute, VMM, what have you. Access policies are grouped into the following categories. Switch profiles specify which switches to configure and the switch configuration policy. Module profiles specify which leaf switch access cards and access modules to configure in the leaf switch configuration policy. Leaf interface profiles specify which access interfaces to configure and the interface configuration policy. And then global policies enable the configuration of DHCP quas and attachable entity profiles, which will then be used for traffic that can flow through the fabric. AEP profiles provide a template to deploy specifically hypervisor policies, but also can be used for other devices. Let's actually walk through that. So an interface policy group can be seen as a container. It associates to a set of policies. Interface policy groups are interface definitions for access ports and port channels. Interface policy groups consume interface policies and provide them to a leaf interface profile. So as you can actually see, we've created a VPC interface for the policy group, and we've chosen our individual access policies to govern that specific VPC. The port cloning feature provides the ability to copy the configuration and apply it to other ports. So I can take that policy group and I can clone that. That's only supported for layer 2 configurations. It's used for small numbers of individually configured leaf switch ports. It's not for interfaces configured using fabric access policies deployed on multiple nodes in the fabric. The policies that are not supported on a cloned port are attachable entity, access entity, storm control, DWDM, and MACsec. So it's not really something that you should really use, but it's just an option that is there. But if you actually do it, you will actually choose it, give it another name, and you can clone the profile. It's actually easier to just create another profile or reuse multiple profiles. While creating an interface access profile, the infrastructure admin specifies which interfaces to configure. These are the local interfaces that these devices are going to be connecting to. All the interfaces in the interface access profile will be configured using policies selected in the interface policy group. Selectors are thought to provide admin with an easy way to deploy a group of switches or interface modules sharing the same configuration. So I mean, you could assume switch ports 10 through 20 on a set of switches have the same config instead of asking an admin to log into one switch at a time and configure one interface at a time. I can select a set of switches and a set of interfaces and deploy a set of policies, and I can connect all of those together. It does make it a lot easier to actually configure multiple ports with the same access policy. Remember, from module 1, we want to be able to keep those on the APIC and not deploy them, because one, you'll use up TCAM space, but also you'll get lower health scores. So just remember that it's okay to have this configured and ready on the APIC for when you have additional devices to connect to the fabric. So a leaf switch profile defines which leaves that that the interface policy is going to be tied to. Okay. So on all switches specified by switch access profile, all interface specified in the associated interface access profile will be configured using the policy selected in the interface policy group. Everything feeds back to the interface policy group. And you can actually see we created a leaf profile. We chose, in this case, one leaf, but you guys, this is just a lab environment for our class, but most everybody else is going to have 2 leaves in a VPC configuration. You can copy and paste the port config, don't do that. ACI pools, domains, and AEPs. So now we're getting into the logical configuration of ACI. Okay, the configuration of the access policies requires an understanding of VXLAN and VXLAN namespaces, but namespaces primarily. Access policies also make configuration of port channels and VPCs easy to accomplish. Port channels and VPCs, since all of that is distributed by Anycast, I don't have to worry about creating peer links. I don't have to worry about creating. All I have to do is create a VPC domain and put 2 switches in that VPC domain. Then I can configure my ports. ACI uses VLANs as a segmentation mechanism. The VLANs used between a server and a leaf have local significance, and they are used exclusively to segment traffic coming from the servers. Cisco ACI has been designed so that when using virtualized workloads, you don't have to enter VLAN numbers manually per each port group. So it's basically tagging tagging that traffic for VTEP to VTEP connectivity. In ACI, you create VLAN pools that are associated with domains. VLAN pools are created for both internal to the fabric and external to the fabric. So internal would be physical or virtual machines, and external to the fabric, layer 2 extension. We have to understand, though, VLANs cannot be overlapping on the same leaf switch, so I cannot use VLAN 10 on ports 1 and 15. VLAN pools are consumed by physical or virtual VMM domains. So remember, VLANs are used between server and leaf, have local significance. VLAN pools cannot overlap on the same leaf switch unless you configure the per port VLAN feature is enabled in the layer 2 policy. That, however, is going to reduce the total amount of VLANs that you are going to actually be able to utilize on a leaf switch. So here's how we create a VLAN pool. We'll create a VLAN pool. So there's 2 choices, dynamic or static. Okay. We have to remember that VLANs in ACI don't have the same meaning as VLANs in a regular switched infrastructure. The VLAN tag is used purely for classification purposes. Traffic is mapped to a bridge domain that has a global scope, so local VLANs on 2 ports may differ even if they belong to the same broadcast domain. Further, mode VLANs can be used to segment traffic into EPGs, but again, they have local significance on a link. So what you would specifically do is you would choose dynamic allocation for a VMM domain, which would be multiple port groups for multiple subnets. From a typical layer 2 perspective, though, if you were doing a layer 2 extension from an existing 5K or 7K, what have you stack, you would still tag that VLAN traffic as ingress, and you would tie those EPGs to the static encap for that specific VLAN tag. So you would use a static pool for anything other than hypervisors. You would use a dynamic pool for hypervisors. Port local scope applies to VLAN significance at the port level. Again, same VLAN cannot exist on the same leaf switch, except you can turn on per port VLAN. That will actually reduce the scope for VLANs on a specific leaf switch. So what we want to do is we want to have global scope default, switch VLAN's significance, prohibits reusing the same VLAN on different ports for different EPGs. Scale is going to be your primary issue with per port VLANs. So if we think about domains, the concept of a domain, here we've got physical and external. Whether you connect physical or virtual servers to the Cisco ACI fabric, you define a physical or a virtual domain. Virtual domains reference a particular virtual machine manager, so in this case it's going to be vCenter, and a particular pool of VLANs or VXLANs that will be used. A physical domain is similar to a virtual domain, except that there's no virtual machine manager associated to it, so it can be a layer 2, can be a layer 3, can be a bare metal server. The person who administers the VLAN or VXLAN space is the infrastructure administrator. The person who consumes the domain is the tenant administrator. So the infrastructure administrator associates domains with a set of ports that are entitled or expected to be connected to virtualized servers or physical servers through an attachable entity profile. Yet you don't need to understand the details of the AEP except that it encapsulates the domain. So so an AEP is a pretty kind of fun concept because you can use an AEP for multiple devices. You can use it for physical domains for layer 2, layer 3. You can use the same AEP for bare metal servers, even for hypervisors. But what you should do is you should have some sort of actual separation by workload. Generally, layer 2, layer 3 devices will have an AEP. Bare metal servers will have an AEP. And VMMs, vCenter and hypervisors will have a separate VMM domain. Remember, there's no concepts of domains in NXOS. The closest similar thing would be to VDCs. But physical domains are used for devices attaching to the fabric. And here's the actual, again, the configuration policies. All this configuration's been done. It's all tied at the AEP. Once the VLAN pool is configured and the VMM domain has been bound to the AEP, then you attach the EPG, you apply the EPG to the VMM domain, and in this case in vCenter, port groups get copied down. So what we have to do is we have to associate the AEP and VLAN pool in the dialog. We have to create the physical domain. So you will create separate physical domains for separate devices. You will tie that to an attachable entity profile, and then you will tie it to a VLAN pool. And then the AEP will represent the group of external entities with similar infrastructure policy requirements. The infrastructure policies consist of physical interface policies such as CDP, Link Layer Discovery Protocol, MTU, LACP, and AEP is required to deploy VLAN pools on leaf switches. You will never get traffic to flow because remember ACI is VLAN tagged throughout the fabric unless there is an AEP. So it is required to deploy VLAN pools on leaf switches. So static pool or dynamic pool, it doesn't matter. An AEP implicitly provides the scope of the VLAN pool to the physical infrastructure. No traffic flows unless an EPG is deployed on the port. So if I don't have an AEP configured, I can deploy EPGs all day long. They're not going to deploy and they're going to fail. So without an AEP VLAN pool deployment, a VLAN is not enabled on the leaf port, even if an EPG is provisioned. Hence, you will get errors, you will get NW issues, and you'll be able to go down the troubleshooting tree. So think about it like this. AEPs provide VLAN access control, interfaces, or VMM domains. In the fabric access policies, the infrastructure administrator will carve up the VLAN space into multiple physical domains, and it's then at the tenant admin that we will tie those EPGs to the VMM or physical domains. So here, under the create attachable entity profile, we'll give it a name and a description. If we want to extend the fabric to the AVE, the application virtual switch, we can enable the infrastructure VLAN, or if not, we'll just tie it to the domain profile. Leaf ports are associated to only one AEP, so I can't have leaf ports on leaf 101, ports 1 and 2 have multiple AEPs. Associating overlapping VLAN pools to the same AEP is prohibited, remember, because of unless we turn on per port VLAN. VLAN provisioned and enabled to leaf switch upon LLDP discovery or on static binding. So here's the fabric access policies configuration examples. I'll just let you take a look at that, but you can actually see that we have multiple AEPs and policy groups for connected devices, domains, VLAN pools, and VLAN range. We will pre-provision VPC logical pairs for each leaf pair. As part of the initial configuration, you'll divide your switches into VPC pairs by creating a VPC explicit protection group as well. And generally, to apply a configuration across a large number of switches, we'll define switch policies and profiles into a single policy group. In this way, large numbers of interfaces across the fabric can be configured at once. So in this case, switch profiles can contain symmetric configurations for multiple switches or unique special purpose configurations. The following figure shows some of the process. We've got switch profile 1, so we've got switch profile 1 for leaf 1 and 102, the VLANs that are allowed, and the specific policies that are configured from a physical level. From a logical level, we've got our interface policies bound to our leaf policy group, leaf interface profile, switch profiles then tied to an AEP, and then a VLAN pool. VPC in the ACI fabric. So, we always want to get rid of spanning tree. So the first step came with virtual port channels. A VPC allows a device to connect to two different physical Cisco Nexus switches using a single logical port channel interface. Prior to VPC, port channels generally had to terminate on a single physical switch. VPC gives the device active-active forwarding paths. Because of the special peering relationship, spanning tree does not see any loops, leaving all links active. To the connected device, the connection appears as a normal Cisco port channel interface requiring no special configuration. That's why we love VPC. But in ACI, there's no peer link required between leaf switches. That's actually handled by the fabric services via Anycast. So peer communication happens via the fabric peer keep alive. Path recovery also happens via the fabric and not peer links, so we don't have to configure that either. Multicast forwarding will determine which peer will actually forward a frame. So if you can see that traffic within the fabric is sent to the VPC Anycast address, traffic is both sourced and destined to the Anycast VPC VTEP address from the remote leaves. So at this point, at the hardware level, flow hashing between the peers via the spine. Spine determines which peer forwards a specific flow downstream to the attached device. And that's also maintained by the Council of Oracle Protocols. So that runs on the spines to ensure all spines maintain a consistent copy of endpoint addresses. So if we have a link go down or a leaf go down, the bounce entry created will be pointing to the peers VTEP for endpoints reachable via the port channel. All MAC IP to leaf bindings for specific VPC are removed from kube database on the spine proxy. On the failure of a peer, the remaining leaf converts all VPC ports to non-VPC local ports. However, they will still keep running. And then when the other leaf comes back up, standard operating procedure at that point. We divide leaf switches in the logical VPC pairs. So in this case, this is very easy to create in multiple VPCs. You can go to virtual port channel default. You can give individual names, and then you can tie your switches together in a VPC configuration. 101 and 102, the ID and IP address. And here's some FEX VPC supports for now and going into the future full mesh. And there's more exciting stuff coming up that I can't really tell you about, but a lots more exciting stuff coming. Troubleshooting access policies. So generally, the picture illustrates the relation of components that define the association of the port with the VLANs. That is the primary sole issue that you're going to run into in ACI, faults or not. Now, if you have something that's not configured correctly, just like you've done in UCS, if you configure a service profile that's not configured right, you're not going to find out about it until you actually deploy that service profile onto the blade. Same thing here. Faults are not generated until the EPGs have been configured with domains, and we've applied those EPGs. So where would you actually need to troubleshoot more often? Okay, some common AEP VLAN errors. If an EPG deployment fails for any reason, faults will be raised on the given EPG. Remember, in the prior modules, we talked about the operational tab. In invalid VLAN, the EPG is associated to domain using an NCAP not defined in that domain. That could be an incorrect VLAN, could be an incorrect VLAN pool, or an invalid path. The EPG is associated to a domain and is using a port channel that's not part of that domain, or an invalid path. So where would we look? We would look at AEP, and we would look at the physical domain. Some things that we do need to know is that ensure no two domains are deployed on the same leaf with associated namespaces or overlapping NCAP ranges, in which case we would have to actually fix that. Breakout cables, these are the approved breakout cables for specific leaf switches. And here's some guidelines for the dynamic breakout ports. Some guidelines and restrictions. I won't read those out to you. There they are. You're more than happy to pause the video and actually go through that. Configuring port profiles, uplink and downlink conversion is supported on 9K, that on EX or FX switches. Port tracking policy, uplink failure detection can be enabled in the Fabric Access Global Port Tracking Policy, so that can actually be configured under Fabric External Access Policies, Global, and Port Tracking. So again, we want to actually be sure that that if we're actually having a problem with our breakout cables, that we cover that. Here's some more port tracking behaviors. And this is not something that I actually cover in the class. Not very many people run FCOE, but FCOE is supported in the ACI fabric. So here's a topology for connecting a 5K or an MDS to a leaf switch. And here's the FCOE support in ACI Fabric as of 2.3. There are later updates. We've actually pushed it to 4. ACI topology supports FCOE. We have to set up a separate VLAN connectivity for SAN host to broadcast FIP and discover F ports on a leaf switch. So we do have to actually have that configuration done. And here's how you would do that on the FCOE configuration. Again, you'll have to create a leaf switch policy group. And then, of course, we have to change the policies that apply to that FCOE enablement. We have to do PFC, fiber channel interface policy, and we also have to do slow drain policy as well. And there's the leaf interface policy group. So port mode would be F, trunk off, and idle, speed auto. And under fabric configuration options, APIC provides a quick start wizard to simplify the workflow for fabric access policy configuration. Start with a quick start under external access policies. You know, really, if you're going to troubleshoot this, you're really not going to want to pay attention to wizards in ACI. I'm a UCS instructor. I like wizards. I like wizards a lot. They work very well. But in ACI, it can cause problems later on down the line, especially with naming configurations. You need to understand the policy model and how to create the policy model manually before you can actually go in and actually perform well enough in the wizards. It can just create problems. And that's just my personal experience. That is what I'm saying here. I would much rather you learn how to do it manually so that you will understand the policy flow and where to troubleshoot.